All right, we are now in session 4 and 5, kind of mashed together. We had an ice storm last Wednesday, so a lot of power outages, and we missed class. So we're gonna put both of them in today's session. I think that we're gonna be able to do that. I think it's achievable. So for the first section of content, we're gonna talk about regression metrics. Up until this point, we've only talked about classification. So we've talked a lot about fraud if we're predicting 1-0, binary classification. We've talked a lot about predicting spam, but we're going to come back to that example of what if we're looking at house prices? What if we're looking at salary? What if we're looking at something that's a numerical scalar variable? These are our regression problems. If you remember, think back to the other course, we talked about regression problems versus classification problems, and we had kind of that tree that had different subsets of problems. Here we're going to talk about regression. So when we have a regression problem, how do we evaluate that? So we're going to talk about the mean absolute error, the mean squared error, the root mean squared error, also adjusted R squared and the R squared value, and prediction error plots. All these squared errors are kind of different manipulations on the same metric, but there's pros and cons to each, and there's many other metrics that we can use for regression as well. But I think settling in on a grounded understanding of mean absolute error, mean squared error, root mean squared error is going to give you enough information to continue to explore those other metrics. So if we can look at the trade-offs between these three, it's a strong foundation and a good place to start to look at the other ones. So let's get started. Okay, so regression, just to reorient, because for the last 3 lectures, we've been talking about classification. In machine learning, regression is the type of problem where we're doing supervised learning. So we're not doing unsupervised learning, not the clustering algorithms, but we're doing supervised learning to predict continuous values based on input feature. So the y equals mx plus b, the y output would be like price of a house. We're trying to predict the price of a house. So the difference between, I'm going to draw on these slides. The difference I want to highlight here when it comes to evaluation is when we're predicting binary classification. Let me just call it class. When it's a classification problem, we have P, what did we predict? And then, I guess maybe I should have called that, sorry. We have Y hat, it's a better term. And then we have Y, what was the actual outcome? And if you guys remember, last time we whiteboarded and we said, oh, well, we predicted 1 and it was actually 0. And so we can say we were incorrect. Or we predicted 0 and it was actually 1. So we can say we're incorrect. Or we predicted 1 and it was 1. We can say we were actually correct, right? When we're looking at regression problems, the reason we need different metrics here, why can't we just use the same ones? All right, let's try to use the same ones. Let's say we have Y hat, and we have Y. And let's say we're trying to predict salary, and it's $100 an hour. So we predicted 100, but the answer was 99. Were we right? Were we wrong? Is this yes? Is this no? Let's say we're wrong. Let's say we're wrong. Let's say this is the wrong answer. Let's say we said, nope, you were wrong because you didn't have exactly the correct answer. Okay, well, what if the answer was 100 and we said 1? Are we still wrong? I mean, we're still wrong, but are we equally wrong? Are we just as wrong on that one as we were on this one? So this is why we need different metrics. What we want to measure is how incorrect we were. So in this one, we were off by 1. We can call this like our residual. I'm not going to write it all out. We were off by 1, and in this one, we were off by 99. Obviously, the goal is to be off by 0. So when we look at regression metrics for evaluation, this is why they're different. Just different applications for regression. So of course there's financing as we're looking at forecasting. Forecasting is a really big domain for evaluation on these numerical scalar values. Also headcount, if forecasting headcount, forecasting capacity planning, predicting house prices, demand for goods. What's the demand for purchase going to be over the next month? Marketing campaigns, marketing to different individuals, propensity of a purchase from a dollar amount perspective, not are they going to purchase, but how much are they going to purchase? Healthcare patient outcomes when it comes to scalar values like measuring blood pressure, heart rate, etc. Resource utilization, like I said, head count, capacity forecasting, hospital bed occupancy, that was really big during COVID, emergency department visits, etc. Just to ground in the 2 models that we talked about last time in last course applied to regression, we talked about linear regression. This is our y equals mx plus b equivalent. And we also talked about decision trees. We talked about decision trees primarily as a classification problem, but you can actually use decision trees for regression as well. There is a decision tree regression algorithm. Okay, let's look at our first calculation here, mean absolute error, MAE. The mean absolute error is typically referred to as the average magnitude of errors, and I think it's the most natural metric that we can think of when we're trying to evaluate how correct are we or how off are we. It's a really simple and intuitive measure here, and it's exactly what I did. And I'm going to whiteboard. It's exactly what I did with the. I still can't figure out how to lock this thing. Anyways. It's exactly what I did with the that problem on the previous slide. Okay. So mean absolute error. I'm going to write them all up here. Equals 1 over n. And it's the sum of the absolute value of yi minus y hat at I. Okay, so if we have y, and we have y hat, and we have, here is our example, 99, 1, 50, 55, 50, 45, and I'll just do one more 50 here just so we have some, this seems like fairly well balanced here. All right, so we've got some values that we want to evaluate for mean absolute error. What that would look like, and yeah, right here. Okay, so this is going to be the absolute value of 100 minus 99 which equals the absolute value of 1, which equals 1. So this one's 100 minus 1, which equals the absolute value of 99, which equals 91. Why do we need the absolute value here?
Which one were you pointing at?
In the formula, why do we need the absolute value? Why can't we just do y minus y hat? Also, this marker is terrible. I'm going to continue this in blue. Okay. Let's look at that. Let's try not to use the absolute value for these two here, 50 minus 55. Let's do 50 minus 55 is equal to negative 5, and 50 minus 45 is equal to positive 5. Okay, so we're off by negative 5 here, off by positive 5 here. 50 minus 50 is equal to 0, so we did perfect on that one. All right, so the next step of the formula is once we get these values, we have 99, negative 5, 5, and 0. We're supposed to add them all together. So that's what the sum says. Sum each of these. So do y at I. So this is I is 1, 2, 3, 4, 5. So sum I at I for index 1, then for index 2, 3, 4, 5, so, and then add them all together and divide by n, where n is 5 because we have 5 of these. Okay, so let's do that. So now we're going to take 1 plus 99 minus 5. I'll do plus negative 5 plus 5 plus 0, all divided by 5. So we have 110 divided by 5. What's the problem with that if we don't take the absolute value here?
The 99 is going to throw it way off.
So the 99 is how off we were from 100 to 1. But if we don't take the absolute value here, the overall goal of the mean absolute error, maybe I should talk about that. We want to minimize this. So our goal is to minimize this. Perfect state is 0. In this case, we predicted 55, but the answer was 50. We should be penalizing the model by 5. It was off by 5. In this case, we predicted 45 and the answer was 50. We should be penalizing the model by 5. It was off by 5. Both of these situations, we should be penalizing the model in equal amounts. What's happening is if we don't take the absolute value, we end up with a negative 5 when we overpredict, and we end up with a positive 5 when we underpredict. Then when we add all of those together, the negative 5 and the positive 5, they actually cancel each other out. So it looks like our model is doing better than it is. We don't want that. We actually want the absolute value here. That's why that's in the formula, mean absolute error. So that becomes plus 5. So then, otherwise, it would be 100 over 5, which is going to equal about, what is that? 5 goes into 120 times. Instead of being 110 over 5. So we're overinflating our performance if we don't use the absolute error, because what happens is they can cancel each other out, basically. So if we had a model, I'll do one more example here. If we had a model and this was perfect, like what we're trying to do, and it predicted equally over and under, and we didn't take the absolute value, all of these would cancel each other out. Our +5, -5, or +5, -5, +5, -5, etc. And our error could theoretically be 0. And it would look like we had, from a metric standpoint, it would look like we had a perfect model. But we don't want that. We want to take the absolute value. That way, the error isn't 0. Everything's just 5, not plus or minus 5. Everything's just 5. And then we add all that up. And the error is going to be like an average. The error will actually be an average of 5. Add all that up, divide by the number of, if we're off by 5 every time. Does that make sense? Why we need the absolute value sign?
Yep, I had to Google absolute value because I haven't taken a math class in a long
Oh no,
time.
you're good. You're good. The reason I'm explaining this is because the nuance between mean absolute error, mean squared error, and the root mean squared error are all around this concept of how do we make sure that the negative values and the positive values don't cancel each other out. So this is one method we can do. We can take the mean absolute error. Okay, back to the slides. Here we go. So we can take the mean absolute error. My coffee's kicking in, guys. Feels great. So the mean absolute error, it represents the average magnitude of errors. So it's the average magnitude of the errors that the model presents. So when we looked at that example where every time you were either over by 5 or under by 5, on average, your magnitude of error is 5. In this case, each time we talk about these metrics, we always talk about how to interpret them. Are we trying to minimize them? Are we trying to maximize them? In this case, a lower mean squared error indicates a better accuracy, or better, I shouldn't say the word accuracy, better performance. So this is a metric that we're trying to minimize. When you look at accuracy, F1 score, precision, recall, those are metrics that we're trying to maximize. We're trying to minimize this. So when we look at error, mean absolute error, mean squared error, root mean squared, anything with error, it's about a metric that we're trying to minimize. So this is the most basic and straightforward metric. When I think of just, hey, we have a regression problem, what's the equivalent of accuracy for regression problem? My mind goes to mean absolute error, the magnitude of errors. It's fairly robust since it considers the absolute differences between predicted and the actual values, sorry. And the advantage here of this metric is that it's on the same scale as the target variable. What I mean by that is you'll see how this changes with some other metrics as we move forward. But if the error is 5 and we were doing house prices, you could interpret that as on average, we're off by $5 on a house price or off by $5,000 on a house price. Not all metrics that we look at are on the same scale as a target variable. So that's a really important thing to pay attention to as you look at metrics for regression problems. Okay. Let's look at this data set. Can you guys calculate the mean absolute error?
Is it 2?
It is 2. Nice. I tried to give pretty straightforward numbers here. So to calculate this, we're going to take the absolute difference. So 20 minus 18, 30 minus 28, 40 minus 42, etc., which ends up being 2 for everything. So your average should also be 2. So this means on average that the predicted value deviates from the actual value by 2 units, whatever our unit is that we're measuring here. Okay. Questions, thoughts, comments, mean absolute error? All right. Mean squared error. Here's our second one. The mean squared error is the average squared difference between the predicted values and the true values. So we're going to compute the squares between each value and then take the corresponding actual value. So let's put this one up on the board. Okay, mean squared error. One over n summation, which again, remember, that just means we take the average. And we're going to take y at I minus y hat at I. But instead of taking the absolute value, we're going to square it. Why are we squaring it? Why would we square this? Y minus y hat.
It emphasizes errors.
Ooh, that's a good point. It does emphasize errors, actually. That's not what I was thinking of, but it does do that. Yeah, let's look at that. Good point. What I was thinking of was that if it cancels out the negatives again, so we're not going to have this problem where if it's, let's just walk through this. So let's do MFC. So we have 199, so we're going to take 100 minus 99, which we already said was 1. But instead of taking the absolute value of 1, we're going to take 1 squared. This marker's terrible. Which equals 1. That's better. This one's going to be 99 squared, which is going to be quite a large number. This is 5 squared, which is 25. This one's, this is 50 minus 55, which is going to be negative 5 squared, which equals 25. And this is 50 minus 45, which is going to be positive 5 squared, which also equals 25. So the reason we're squaring here is because a negative times a negative is a positive. So when we take a negative squared, we're always going to get that positive number. So we don't run into that issue. Remember, we're trying to avoid canceling out that picture we had. We're trying to avoid, what if we were off by 5 every single time, but it would just alternated between over and under? We're trying to avoid having the errors cancel each other out. And making our performance look better than it is. Okay, 0 squared is 0, and then we would just sum all these together. It would be 1 plus 99 squared plus 25 plus 25 plus 0 all over 5. So that would be our mean squared error. Let's calculate this, because actually I want to show you something. 1 second. Actually, where's that eraser? An important point here, I think, that I don't want to skip over. Okay, so this one, this is 22. This is 110 over 5. Oh, 22, okay? So we could say, like, on average, we're off by like $22 if we're predicting. I think we said we're doing salary. It's monopoly money though.
9801.
Thank you.
Mean squared.
Perfect. So that's 9801. So this is 9801 plus 51, 9852. All right. So we can't say that we're off on average by 9852. That's not what's going on here. So this is not as interpretable in terms of how to measure this or how to communicate this back. On this one, it's really easy. We can just say, oh, on average magnitude of errors, this is the average squared difference. So this is in squared values, essentially. But what it does do, whoever cleverly said that, you are correct, is it overemphasizes when we're off by this 99, whoa, we got a really big number. What if we change that 99 to like a 1? Then the answer is going to change to 52, right? So the huge difference between these, like massive difference. So what, let me put this back. So what the mean squared error does is it does place more penalty, and I probably have this in a later slide, so I'm jumping ahead of myself. But it does place more penalty on the errors that are off by quite a bit. So it's sort of like log loss. You know how log loss penalizes overconfident predictions, heavily confident predictions. This is sort of like that for regression problems, where you're going to get more penalty on being off by really large amounts. Okay, so computes the squared distance. I think we covered that. Interpretation here. So of course, a lower mean squared error, all the error metrics signify a predicted value that's closer to what we want it to be. If it's lower, we're trying to minimize error. We don't want to maximize error. The difference here is that these are the squared units of the target variable. So when we looked at that 9852, those are squared units of dollars, for example. A very natural question might be, can't we just take the square root of that? And that's actually the next metric we're going to look at. But a couple of trade-offs here is that squaring the differences, as somebody pointed out, emphasizes larger errors more than smaller ones. So you're creating a reward function for your model that's placing more penalty on making egregious errors that are off by quite a bit. So you're rewarding more conservative models that place conservative bets on their predictions, essentially. Okay, can you calculate the mean squared error?
It's 4.
I got 4 as well.
It is 4.
Okay.
I made these easy. I didn't want you guys to have to do each one. But
Sometimes when they're too easy, it feels like they could be wrong.
making you guys second guess yourselves. Yeah, this you should be able to look at. Just emphasizing here that if you're, 20 minus 18 or 40 minus 42, these are canceling each other out. I think the point I'm trying to make here is this doesn't end up being -4 and +4, whether you're over predicting or under predicting, because we're taking that squared value, we're still getting a positive number that we're then summing. Okay, one more and then I'll give you guys a break here. Root mean squared error. So I think you guys you've kind of got the pace of this, right? We did absolute error, and then we did, we squared it. We tried a different way of not canceling out the negatives. Now, a natural question, like I said, is, well, what if we just took the square root of that? So root mean squared error, or RMSE, this is probably one of the most common, one of the most popular metrics that I see used for a regression problem. This is the one that I see everybody go to, just like as a baseline on just regular RMSE. So RMSE, we have 1 over n summation, so just the average of y minus y hat squared. So it looks exactly the same as our mean squared error. We're just going to take the square root afterwards. So let's get this one up on the board. Okay, let's do RMSE. Exact same formula. We're just going to take the square root. Here we are. So we don't even have to do anything over here on, I mean, theoretically we could take, so if we did RMSE, we could theoretically take the square root of each of these, but we're just going to skip to the end. We're just going to go dot, 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 and we're going to take this formula, and we're going to take the square root. So we're just going to take the square root of 9852, which is, I don't know, I have to look it up. $99.
Aren't you supposed to divide it by 5 first and then square root?
You are right.
9852 divided by 5 is 1970.4.
Thank you. I should have done that on this other one. 1970.4. Thank you. And this should be 1970.4. I thought 99 sounded very incorrect, so. All right, square root of 1970.4.
44.38.
Excellent. All right, 44.38. Okay. Same data, same problem, 3 different ways of evaluating it, 3 different metrics that we could choose for how to pick a model. And it matters because either we're rewarding the model with this function, or we're rewarding the model with this function, or we are rewarding the model with this function. And they're not the same. I will say these two, mean absolute error and the root mean squared error, are in the same magnitude, same scale as whatever we're measuring. So let's just say these are dollars. We can say on average our model was off by $22. Or we can say that the average square root of the average square root of the squared differences was 44. So we can say on average we're off by $44. Different metrics, and we got, this one seemed a lot higher than this one. The reason this one's, why do you guys think the root mean squared error is so much higher than the mean absolute error in this problem?
Because it doubled or squares root, took the square of 99, which emphasizes more of an error, right?
You got it, 100%. You guys are tracking so well. So because we had this really, really large error here, the the metric is penalizing that more. So it's coming as represented in this score. So that 44.38 is representing that larger magnitude. Perfect. Now you guys can explain that to stakeholders. Hey, we chose this metric because in the problem that we're working on, we want to penalize the model being off by more. So we chose the root mean squared error. Or maybe you don't care. So you chose the mean absolute error. Or maybe the mean squared error was good enough for you. So you chose that one. I don't really see people choose the mean squared error a lot because of the interpretability piece. I usually just see them gravitate to the RMSE. Okay. So interpretation here, the RMSE provides a measure of the average magnitude of errors. So average magnitude of errors as opposed to just the average errors. So this is representing when you're off by a lot, that magnitude plays a really big factor. So again, main advantage here, same units as the target variable. So if you're off by X dollars, RMSE will actually be in dollars. Okay. Obviously, outliers, because if you have some extreme outliers, so if we're looking at house prices and we've got some billion-dollar mansions in there and our model just didn't do well on the billion-dollar mansions, but it did well on the other houses, those outliers could heavily skew the RMSE. So compared to mean absolute error, this is just a trade-off you have to choose. Do you drop those outliers? Do you change your metric? These are decisions that you guys have to make. And that's why you're making that decision in assignment 1. You're looking at a problem, a scenario, and you're figuring out what is the metric? How do I evaluate this? All right, can you guys calculate the RMSE here? I think it's not a trick question.
2.
It's 2. Excellent. All right, this is for you guys, just a slide comparing them all. This is just the beginning, by the way. There are many, many other metrics. These are not by any means the only 3 metrics or manipulations that you can use to compare scalar values, basically regression problems. But I think now you have enough of a foundation to understand the trade-offs between these. And I think it gives you enough of the sense to look at other metrics and question things like, oh, how does magnitude of error impact this metric? How do outliers impact this metric? How does this metric handle not canceling out positive and negative values when we're summing up the errors? So this is all I have for means absolute error, squared error, and root mean squared error. We're going to take a short break here, and then we're going to come back and we're going to talk about R squared and adjusted R squared, which I think are useful if you guys are reading any research papers. That's where I see them a lot. Not as much used in enterprise work, but I do see them on research papers, and they're helpful to know. So, all right, let's take 7 minutes, and we'll come back. All right. We also have a breakout here. That is we go to regression metrics, and I'm going to download these so they are, we're not editing those. Let's talk R squared. But before that, let's do absolute error. All right, let's spend a few minutes on this breakout here. We're going to calculate the mean absolute error, mean squared error, and root mean squared error for these model predictions. So let's write a function. Let's just do this together. It'll just take a moment. Okay, let's write a function that calculates the mean absolute error. So we want to take y minus y hat. So let's make a y pred is equal to, that's fine, y pred and y true. Let me make sure these are not correct. There we go. Actual, oh wait, that is correct. 30, 40, 50, 60, 22, 28, 42, 48, 62. That looks good. Okay, so we have y pred and y true. Now we want to create a Python function that calculates the mean absolute error. MAE. We're going to take in y true and y pred. And that's fine. Okay. So first we're going to set total error equal to 0. And then for each item in our list, we're going to iterate over y true. And we're going to take the absolute value of y true at I minus y pred at I. Then we're going to take that total error, save it into the mean absolute error, and divide by the length of y true. Let me put these in different cells. Here. Let's try it out. Would help if I made that a function. Here we are. All right, 2.2. Let's make a calculate MSE. Our total error, we're going to start at 0 again. We can actually let's start from this starter code here. But instead of doing MAE, we're going to do MSE. And instead of taking the absolute value, we're going to take the square root, which probably means we need to import something, probably from math. Import square root. There we are. So instead, oh, not square root. I'm sorry. We're squaring this. In Python, to square things, we use 2 stars, two asterisks. So instead of taking the square root, we're going to take this times 2, and that should give us the MSE. Y true, y pred, and that's 5. All right, so now we're going to use the square root function. Let's make a function that instead of doing MSE, does the RMSE. So we can take MSE, and then we can just say RMSE is equal to the square root of MSE, and we're going to return our MSE. Calculate our MSE, pass Y true, Y pred, and now we have 2.23. Okay. Back to any questions here? It's the same stuff we pretty much did on the board, just codified. Back to our content here. Next thing we're going to talk about is R squared, which is known as the coefficient of determination. You might hear it referred to as that. And it's a statistical measure that represents the proportion of variance in the dependent variable predicted from the independent variables in a regression model. Sometimes it's referred to as the goodness of fit. There could be a question of how good of a fit that your model is to the data. I have to cough 1 moment. Here's the formula. It's a ratio of the explained sum of squares SSR. It's the SSR over the SST, which we're going to talk about. We're going to do a formula for the SSR, and then we're going to do a formula for the SST. And it's 1 minus that is our R squared. So this probably looks familiar to you. The SSR is the sum of squared differences between the predicted values and the dependent variable. So it's the y minus y hat squared. This quantifies the amount of variability in our dependent variable. When we look at the SST, the difference here is this y bar. This little bar over this is called y bar. So SST is the total sum of squared differences between the actual values and the mean of the dependent variable. So this is looking at the average value of the dependent variable. That's the y bar. So this is going to quantify the total dispersion of the values of your dependent variable. So how varied, how volatile are your predictions? When we look at R squared ranges from 0 to 1, and a value closer to 1 indicates that a larger proportion of the variance in the dependent variable is explained by the independent variables in the model. So how much explainability are you getting out of the dependent variables in the model? It suggests a better fit. Conversely, a value closer to 0 indicates that the model explains very little dependence on the variable. Notice we're not really diving too deep into R squared, too nitty gritty. I want you guys to be exposed to it. I want you to be aware that it exists. I want you to know how it's calculated. The y minus y hat over the y minus y bar, both squared. I want you to know how it's calculated. I want you to be aware of it. So as you are reading documentation, as you're reading research papers, as you're reading about new things that are coming out and the R squared values that they're reporting, you're familiar with it. We won't leverage it a ton in this course, and I haven't really seen it utilized substantially in when you're actually training a model to implement into production. Typically, people care more about what's the performance you're getting out of your model. At the end of the day, how are we going to assess value? And it's probably how correct your model is and how often it's that correct. How often is it correct? And how correct is it if we're looking at regression? Is it off by a lot? Is it off by a little? And R squared sort of represents more the robustness of the predictions than it does necessarily the performance of the model. So a little less concerned with that. We do have a breakout in here. Let's take a look at that. Let's go. There's a breakout here. We might skip this and we'll just keep moving here. But there is an R squared breakout if you guys want to play with that. Similar to the R squared, there's another metric. Just like we have mean squared error, mean absolute error, root mean squared error, which are manipulations on that mean absolute error calculation. We also have the adjusted R squared, which is a modified version of our R squared value. So it adjusts for the number of predictors that you're putting into your model. So it provides a more reliable measure of the model's fit with multiple predictors. So it takes into consideration, do you have one feature that you're using? Do you have 4 features that you're using? Do you have 10 features that you're putting into your model? So here's the adjusted R squared formula, where R squared is 1 minus R squared n minus 1 over n minus k minus 1. So n is the number of observations. This is your sample size. And k is the number of independent variables in your model. So adjusted R squared takes into account how many features are you using to make that prediction. Also ranges from 0 to 1, and an adjusted R squared value that's closer to 1 indicates a better fit for your regression model. However, the R squared value takes into account the number of predictors, so it penalizes you putting in more predictors, more features that don't provide explanatory power. So if you just keep adding features to your model and they're not really adding a lot of lift, it's just more information with not a lot of value, you're going to get more penalty out of that from an R squared perspective. Like I said, in practical implementations of machine learning, I do not see people focusing as much on just only add features that add a lot of lift. I see them saying, oh, let's add a feature, even if we get a small amount of lift, that's even better. We can increase our automation rates. We can increase our ROI. We can increase our output here. So this kind of goes away with the law of large numbers and the central limit theorem. So, but it exists. It's out there. I want you guys to be exposed to it. You may run across it. It's very common. It's very common. There's also prediction error plots, known as residual plots, that you guys can use to graphically represent the performance of your model. So when I was drawing on the whiteboard, I said we were off by 5. You can use these prediction error plots to plot something called your residuals. And maybe I realize now that I should have put this residual terminology at the very beginning of the PowerPoint, and I'll take notes for that for next semester. But when we were whiteboarding, we said the absolute value of y minus y hat, that's our residual. So a residual is known as our prediction error. So this is the difference between our observed. Let me draw. All right. So here is reality, and the dots are going to be our predictions. We predicted here, we predicted here. So each of these have residuals associated with them. So y is, like I said, y is the line, and y hat is what we predicted here. And the residual is the difference between y and y hat. So these lines to these dots, these are the residuals. And sometimes it's represented as E sub I. So we could have done the absolute value of E sub I, and that's our mean absolute error. We could have done E sub I squared, and that's our squared error. We could have done the square root of E sub I squared, and that's our RMSE. So it's a residual, just a terminology thing here. And it represents the deviation of each point from the model's prediction. Oh, yep, so this is the last slide here. So we can just make plots that represent that. I will keep these annotations, drop this as annotations in the folder. All right. Any questions so far? Should we move right on to multi-class classification? All right, for the life of me, I cannot find my PowerPoint for this. I have the PDF, but not the PowerPoint, so I have to keep looking for that. So annotations, can I draw on this? Oh, I guess not. We won't be drawing on this because I don't have. Okay, multi-class classification. So we're going to move back to our classification realm. So we talked about regression. We talked about metrics in terms of quantifying how incorrect we were relative to house prices or relative to salary or relative to scalar amounts. Now I'm going to ask you to context switch back to the world of classification. So we're predicting yes, no again. Either it was right or it was wrong. It was a cat or it wasn't a cat in the image. And what we're going to talk about particularly is not just binary classification, but we're going to talk about multi-class classification. So you guys feel pretty good about binary class classification these days, where we can do F1 score, accuracy, precision, recall, true positives, false positives, true negatives, false negatives. If we're saying, it was spam and it wasn't spam, you guys can build out all of those confusion matrices. What if there's more than one class? Remember our number problem from last semester where we had a neural net, we were building a deep neural network, and we had different numbers that were labeled. We had 1, 2, 3, 4, 5, 6, 7, 8, 9. I think it actually started at 0. We had 10 numbers, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. It was by the MNIST, numbers data set, and was developed for the post office to create machines that could read written addresses on envelopes initially. Well, that's a multi-class classification problem. Wish I could draw on here. That's a multi-class classification problem. We're going to erase this. I'll take a picture, drop it in the Slack, but I'm going to erase this because we're going to talk multi-class here. Someday, I will learn how to lock this. Okay.
If there's anything needed to be coded, you're our gal. But if we got to lock a whiteboard, we'll probably outsource that part.
100%. Yes. I really can't figure this out. I need you guys to help me out with that. Maybe we can crowdsource this problem.
YouTube it.
Sorry, go ahead.
We can YouTube it.
I bet we could figure it out. There seems to be a deal here. I can't figure out how to, anyways. If somebody figures it out, 10 bonus points. Really though, so let's do our multi-class classification problem. So we have, let's do multi-class. This is a different problem. So we know, with, I'm just going to do binary over here. Binary classification. We know if we had y versus y hat, if we said it was 1 but it was actually 0, obviously we're incorrect. If we said it was 0 and it was actually 1, we're incorrect. And we know the two situations in which we're correct. If we said it was 1 and it was 1, and if we said it was 0, it was 0. Cool. What about our numbers problem? What if we have these numbers we're trying to predict? 0, 1, 2. I'm just going to put them all up here. 0 to 9. 4, 5, 6, 7, 8, 9. Okay. And what if we predict 0? Obviously we're correct. Okay, but what if it's 1 and we predicted 0? What if it's 2 and we predicted 5? What if it's 3 and we predicted 8? Let me give us some credit here. Maybe we got a few right. Let's just leave it at, we got the rest right, okay? So we were good from here on. But what about these? How incorrect were we? Do we have to? Obviously, we were incorrect. These were wrong. Okay, that's pretty obvious. Do we need to worry about how incorrect we were, and how do we measure this problem? How incorrect we were in multi-class classification? So when the option is we could have predicted a lot of classes, a lot of different classes. And it gets even more complicated when we introduce probabilities with this. Like, what if the probability of 0 was 0.6, but the probability of 1 was 0.4? So that's the background. Let's dive in. That's multi-class classification. So we're going to look at accuracy, which you guys are already familiar with, but how do we measure accuracy when we have multiple classes, especially when some of those classes can have different weights? So we're going to look at macro, micro, and weighted averages. And I find these to be very important I use these all the time. Just used this last week. Somebody was presenting some accuracy performance metrics for a AI machine. And I asked a question about it, whether it was weighted or not. And if it was weighted, was it macro weighted or was it micro weighted? It's important in terms of how we assess the performance across multiple classes, because depending on how you do it, it can change the outcome if you have heavy class imbalance. We'll also look at categorical cross entropy, and we may touch on 1 versus all and 1 versus rest. Okay. So multi-class classification, we already set up this problem, but it's the type of machine learning where our goal is to classify instances into one of 3 or more classes. So when we're creating these decision boundaries now, we are no longer just saying, yep, here's our decision boundary and it's either of class 1 or class 2. We could have multiple classes that we are putting things into. So a more diverse decision boundary here. You guys have already worked with a multi-class classification problem. The IRIS dataset, is a multi-class classification problem where we have the setosa, the versicolor, and the virginica. Multi-class classification problems have an interesting dynamic with class imbalance. You can have a large proportion of classes represent a particular part of the data or a particular part of the problem. So in one of my courses when I was in grad school, I was trying to build a neural network to actually look at spatial images, like images taken from space of terrains of the Earth, and like classify them into certain terrains. And there was a heavy class imbalance on this forested area of terrain that we're trying to predict, because there wasn't a large representation of that in the data set that I was working with. So there was a heavy class imbalance, but on just one area of the classes. So it's important to consider that, and I think you guys will see why when we look at accuracy, precision, recall, and the weighting across of these. The weighting is the main key part I want you guys to take away from this. Okay, let's look at multi-class accuracy. Great, we have multiple classes and we made these predictions. Can't we just add them all together? How does this really change? It doesn't really change a ton. We're still looking at the number of correct predictions over the total number of predictions. So accuracy, high accuracy, model's doing well. Low accuracy, the model's not doing well. And as you guys know, it's a really common metric. I want to get to the weighting here. So if we can look at this problem here. There's nothing surprising in this. So if we have a multi-class classification problem where we're aiming to classify the images of fruits into 3 categories, we have apples, bananas, and oranges. If we are correct 35 out of 40 times on the apples, correct 25 out of 30 times on the oranges, correct 28 out of 30 times on the banana, then we can just add up the number of times that we were correct over all of the predictions that we made. So in this case, number of times we were correct would be 35 plus 25 plus 28. We're going to get 88. Take that over 100, 88%. So multi-class classification accuracy, it doesn't really feel or look that different from binary classification accuracy. What looks different is when we start to build out this confusion matrix. So when we looked at binary classification, our confusion matrix was just 4 squares, right? I should have put a slide in here in between these two. Our confusion matrix, I want to draw. That's not a pen. It's a highlighter. All right. Oh, here we go. All right, I'm almost there. Sit. Yeah. Okay. Keep letting me draw. So when we had our confusion matrix before, interesting, I have to keep hitting this. Sorry. We had, I need to find the PowerPoint. We had 4 dimensions, right? What were the 4 dimensions? Do you guys remember?
Are we talking the like true, false, false, true, false, false?
Yep, you got it.
Okay.
So we had 4 dimensions. I'm going to do here in red. When we were looking at binary classification. So we had our wide red. Or let's just do what you said. I won't even put the axes on here. But we had
TP.
Yep, TP. What was the bottom one?
FN.
TN. Negative.
Yeah, that makes sense. Yeah.
That's That's when TP is when we predicted 1 and it was actually 1. TN is when we predicted 0 is actually 0. And then what's up here?
FP.
FP and down here. F.
FN?
FN, you got it. So these two were correct, these two are wrong. False positive is when we predicted 1, it was actually 0. False negative is when we predicted 0, it was actually 1. Okay, so there was our matrix. It was pretty simple. Now, when we come to look at multi-class classification, our matrix is going to get a lot bigger. Because now it's not just true positive, true negative, false positive, false negative. We have our Y true, and you can do this either way, but Y pred, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. All right. 1, 2, 3. I might have missed a line in there. 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Wow. That's a big confusion matrix. What this is saying is how often, and I made these lines go way out of bounds, so let me just clean that up a little bit. There. Now it looks like a matrix. How often did we predict 0? I'm going to color the green squares correct that are correct squares. We predicted 0 and it was actually 0. We predicted 1 and it was actually 1. We predicted 2 and it was actually 2, etc. So you're going to get this diagonal going across here. I might have gotten off one on there, but you get the idea. When we were correct. All of the other squares are when we are incorrect. So how often were we confusing 3 and 8? Numbers that are going to be, this is a really useful matrix. This is a very useful matrix for multi-class classification problems because it can tell you what you're primarily confusing. You'll be able to look at this and say, oh, when it's actually 8, that's getting the most mixed up with 3. When it's actually, when the real value is 3, that's also getting the most mixed up with 8. So 3 and 8s are getting mixed up with each other. Okay, let's go back to the slides. I think this will make more sense now. Okay, now we can look back at this chart. 9 numbers is a lot. Let's look at 4. Let's pretend we're just looking at 1, 2, 3, and 4 here because 9 is a little overwhelming to just look at right off the bat. So we have predicted and expected. Expected is the same thing as Y true. So we predicted 1, and it was actually 1 52 times. We predicted 2, and it was actually 2 28 times. We predicted 3, and it was actually 3 25 times. And here's the correct for 4. The ways in which we were incorrect, the ways in which we were incorrect are the pink squares here. Where are we most incorrect? Well, when it's a 4, we're actually predicting 3 quite a bit. So we're over predicting 3 for our 4. And when it's actually a 1, we're also over predicting 3. So we're just predicting 3 a lot. This model is just saying 3 very, very often. And it's missing on these 2 spots here. when this is the example that I was talking about with the 9 numbers, when we get to 9 numbers, it can expand even larger here. So here we have, we can say, oh, where this model is very correct quite a few times. But here, when the true label is 4, we're actually predicting 1 2 of those times. And here, when the true label is 1, we're actually predicting 8 2 of those times. So this is how you guys interpret these confusion matrices. You should be able to feel comfortable with these now, looking at these, reading these, interpreting them, kind of drawing conclusions about where the model is making mistakes. Do you guys feel comfortable with this? How do you feel here? It's just a slight expansion on our binary classification model. True positives, true negatives, false positives, false negatives. We're just adding the dynamic of multiple classes that we can be, there's multiple ways we can be incorrect. Let me put it that way. Okay, we're going to get to the weighting. One thing that we can do, so this is sort of how we can look at an accuracy. We can sort of do performance by class here, right? We can look at when we predicted 9, how often were we correct? Or when we predicted 8, how often were we correct? We can also calculate precision by class. We can calculate recall by class. So we can look at, out of all of the instances belonging to the number of 9, how many times did it actually belong to that class? So we can calculate this precision by class as the true positives of class A over the true positives plus the false positives of class A. So we can turn, what we're doing, if you think about it, is we're turning this into a binary classification problem from a metrics evaluation standpoint for each class. So we have 10 numbers, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 10 numbers. You're going to get 10 precision metrics. You can calculate a precision metric for predicting whether it's number 0, a precision metric for predicting whether it's number 1, a precision metric for predicting whether it's number 2. So you can calculate this precision by class. So we can get that, we can create that binary classification metric matrix, true positives, true negatives, false negatives at the class level. So for example, if we're training an email agent and instead of saying, is it spam or not, we're now saying, is it spam or is it normal or is it urgent? We can do that big matrix that we looked at up here, right? We could build that out with 3 classes, or we could build out a matrix for each class. And we could calculate what's the precision of our class 1 urgent. What's the precision of our class 2 normal? Sorry if there's background noise. What's the precision of our class 3 spam? And I think your guys' head is probably going to the next natural thing, which is, okay, well, couldn't we just add all those precisions together, divide them by 3, divide them by the number of classes, and wouldn't we just have something called an average precision? Absolutely. Oh, okay, I don't have PowerPoint on here, so I can't see what the next slide is. I was guessing. I guess I decided to do recall first. Keep that thought. Recall by class. All right, this does make sense to do next because we're already on this topic. Okay, so we did precision by class. Can we expand that to other metrics? What if we just applied all of our metrics that way? Absolutely. You guys are really familiar with recall. which, if you remember, is out of all the instances actually belonging to a particular class, how many were correctly predicted by the model? I always think of recall as how many did we catch? You know, you want to recall them, you want to catch them. How many did we catch? So your typical recall formula, TP over TP plus FN, just apply that at a class level. All right. So what if we want an overall metric? So this is what I was trying to get to. Sorry, I can't see the next slide progression here. So this is great. This is really helpful. This helps us know how is it performing on urgent, how is it performing on normal, how is it performing on spam. Oh, look, our precision on normal's really low, especially compared to spam. Our precision on spam is pretty good. So this gives us a lot of insight. This gives us insight into what the model's doing, how it's making those decisions, how good those decisions are, where it's going to fail, what the risks are. However, this is useful to us as data scientists. However, sometimes you just need to report a number, and people just want one number. They just want to look at one thing. They don't want to look at the performance across these different classes. They just want to know, give me one metric for your model, and how is it performing? To do that, we can, of course, just calculate the overall performance by adding them all up and dividing them by 3. But there's probably other ways that we can do that as well, and it will change the output, and it depends on what you want to do. Depends on what your objective is. We can do macro averaging, micro averaging, and weighted averaging. So let's talk about macro averaging. So the most natural thing to do, what I was saying earlier, is what if we just took all three of those metrics, just added them all together, divided by 3? Yeah, we can absolutely do that. That's a macro average. So we're going to calculate the number of true positives, false positives, true negatives, and false negatives for each and every single class. For all 9 of our classes, we're going to drop that confusion matrix. We're going to calculate the precision, and we're going to calculate the recall at a class level. So this is exactly what we did on this slide. We calculated the precision at a class level, and now we're going to add them all together. 0.42 plus 0.52 plus 0.86 divided by 3, because we have 3 classes. And that will give you a macro average. So a macro average is the average precision or recall across all the classes. Here we go. So we have precision of class A plus precision of class B plus precision of class N divided by N, where N represents the number of classes that we have. This is macro average, precision, and recall. Just off the top of your head, what do you guys think is going to be a potential downside of doing macro average, precision, and recall? So when we're doing a macro average, we're saying that class 1, class A here, has equal weight and equal representation to class B. We're saying class B has equal weight and equal representation to class C. So we're giving each class equal rights. We're saying they're all just as important. We are weighting by class. The risk of that is in class imbalance, essentially. If you have a heavy class imbalance class, let's say I've got a number in my digits, the number 1, and I only have 2 examples of number 1. And so I get them both wrong because I only have 2 examples, and everything else I have 100 examples of. And those I do really well. Well, the performance on, I was thinking about whiteboarding this. The performance on class 1 is 0, and the performance on everything else is pretty good. But I'm going to take a really heavy penalty for being wrong on that very small sample size. And it works in the reverse too. What if I just got lucky? What if I was right on those 2 and I was actually pretty average on everything else? I'm going to overinflate my performance. So the advantage or disadvantage, you could look at it either way, of doing macro average precision recall is that you're giving equal representation to the classes. And that means that classes with small class imbalance get equal small class representation. Classes with small class representation get equal representation in the metric. You may want that, you may not. You have to make that decision. You have to decide if that's how you want to measure things. Okay, so here's a macro average precision and recall. We can take precision here. We can take the recall here. As you guys can see, there's actually 200 records here. There's 8 records here, but that doesn't matter. The performance on those 200 records gets equal representation compared to the performance on those 8 records. Or put another way, those 8 records get more representation than the 200 records in terms of their value that they add to the metric at the end of the day. So whether you want that to be the outcome or not, you have to decide. All right. So in micro average precision and recall, you first calculate the true positives, false positives, and false negatives across all of the classes, and then you substitute that into the formula. I think I have a better, yeah, here. This is a better way of representing that. So we could do it this way. We could say, hey, what's the precision for this class? What's the precision for this class? What's the precision for this class? And average them together. Or what's the opposite of that? Let's go look at all the records. Forget classes. Forget representation by class. Let's just say who was right, who was wrong, add them all up, and then divide by n from a precision perspective. So what if we know the precision formula? So I'm jumping around a little bit here. We know that the precision formula is TP over TP plus FP. So what if we just calculated all the TPs and FPs and then put them into the formula instead of averaging the precision by class? So what if we said what were all the TPs and what were all the false positives by class and substitute them into the formula? So that's what we're doing here. Can we get the true positives of class A plus the true positives of class B plus the true positives of class N all over, remember, true positives plus false positives. So TP over TP plus FP, or TP over TP plus FN for recall. The difference is here that we're still calculating precision and recall. Both of these methods are calculating precision and recall, but this one's a macro average where we're calculating the precision and recall by class. And this one's I'm sorry, I have a typo. This is a micro average, not a macro average. This is a micro average where we're calculating the true positives and the false positives or the false negatives in the case of recall and putting them directly into that formula. So the difference between these two is what's the difference? Like that's what I would be asking. Why does it matter? Why does it matter? We're we're calculating precision, we're calculating recall. It does matter if you have class imbalance in your problem. If your classes are evenly distributed, evenly balanced, which is almost never the case, then it doesn't matter. Here you have to decide, where do you want to apply the weight? Do you want to apply the weight to each class, give each class equal representation, or do you want to give each instance equal representation? So in this case up here, remember where we said if we did macro averaging, that these 8 records here would actually have more weight, more importance in the overall metric than these 200, since we're saying this is worth a third, this is worth a third, and this is worth a third. Whereas if we are going by record, it doesn't matter the class that an individual belongs to, we're giving equal representation to each instance, each occurrence. So micro averaging says, nope, I don't care about the class. I'm just going to give equal representation to every record, and I'm going to calculate directly precision and recall at the record level. The downside here of micro averaging is you run into a different problem from macro averaging. In micro averaging, imagine a situation where most of your data belongs to one particular class. So let's look at our numbers problem, and let's assume that 95% of our data is in the number 9 for some reason. If we just do like pretty well on the number 9, it doesn't matter what we do on the other classes. We can just predict 9 the entire time. We're getting back to our fraud problem here. So the pitfall of micro averaging is when you have heavy representation in one class, this metric will bias that class. So the micro averaging will always bias your majority class. If you have a really heavy weighted majority class, I would recommend macro averaging. If you have severe class imbalance in 1 or 2 classes, you might want to lean more towards micro averaging across all these instances. It sort of depends on the problem and how many classes you have, but pitfall of macro averaging, each class gets equal representation. So performance on small sample sizes can have dramatic impacts on your metric. Downside of macro averaging, it's just bias is given to the most represented instance, the most represented class. So the popular class wins, basically, in terms of its representation in the metric. Oh, maybe I said that on these next slides. Okay. So macro averaging, in summary, macro averaging treats each class equally. That can be a good thing or a bad thing. All classes have equal importance. It's really great on imbalanced data sets in certain situations. It can make the classifier look worse due to low performance on unimportant small classes. Like I said, what if you had a class that was just 2 records? You totally did terrible on them both. You're getting penalized just as heavily for the performance on those 2 classes as you are on your performance for 200 records, where maybe you did pretty good. But also it can disguise poor performance too. What if you did really well on those 2 records and really you didn't do that well across your other records? Micro averaging, on the other hand, overemphasizes, biggest pitfall, overemphasizes the performance on the majority class. So whoever's represented the most, that's basically what your metric is representing. It's representing your majority class. Do you guys want to try this one? This is smaller. I don't have the X and Y axes labeled here. Use this confusion matrix and let's calculate the macro average versus the micro average. Let's say that the X axis is Y true and the Y axis is Y pred. We're just going to pick. Oh, actually, let me look at the answer, figure out what I did in the answer. By the way, do you guys need a break or are you good? We're at 8:10. Okay, we'll keep going, but we're just going to keep going past this example. So here we have a confusion matrix, and if we wanted to calculate the macro average precision and recall and the micro average precision and recall, we would calculate first the precision at each class. Oh, I didn't know that was going to highlight that. So we have the precision at class A is going to be over 10 plus 1 plus 3. So we have 10 is when we're correct over 10 plus 1 plus 3. 1 plus 3 are the two situations in which we're incorrect. So we predicted 10, so y pred is on the top, and y true is on the side. And it was actually, we predicted A, and it was actually B one time. We predicted A, and it was actually C 3 times. So we can take 10 over 14. We can do the same with B, precision of B, calculate it with this slice. Excuse me. 12 over 12 plus 2 plus 4. 15 for C over 15 plus 2 plus 3. So we have our precision here. We can calculate our recalls. So if we're looking at macro average, we can take the average of all of these things. So we can take 0.714 plus that 0.667 plus 0.750. Add them all together, divide them by 3. This is our macro average. Okay, what if we did a micro average? If we wanted to do a micro average, we're going to have to go calculate the true positives, the false positives, and the false negatives across the entire data set. So where are all of our true positives? Well, that's the diagonal. When did we predict the value and it was actually the value? We predicted A and it was actually A. Here is 10. We predicted B and it was actually B. Here is 12. We predicted C and it was actually C. Here's 15. 10 plus 12 plus 15. So these are our true positives. So when we're looking to put that in our micro average precision formula, we can do total true positives over total true positives plus total true negatives. So that's how we get our 37 here. 37 over 37 plus 15. The 15s are false positives. So our false positives is when we tried to predict that number, but it was actually a different number. So 2, 1, 3, 4, 2, 3. 2, 1, 3, 4, 2, and 3. So all the times that we tried to predict A, but it was actually B, or tried to predict B, but it was actually A, or tried to predict B, but it was actually C, you add up all the other numbers. Great, so these two are going to be the same. So that means our micro average precision and our micro average recall are the same. Okay, weighted averaging. So great, we talked about the trade-offs, the problems between the representation by class size. And we talked about, well, we could do macro averaging, where we have equal importance across every class, but then that introduces this problem where classes with small numbers of records get overrepresentation. And then we talked about, well, we could do micro averaging, but micro averaging overemphasizes the performance on the majority class, and it just says whoever's the biggest representation, they get the most credit. That doesn't really seem like the right way to do it either. Well, we could do weighted averaging. So here's the balance between the two. This is what I recommend. Weighted averaging. This takes into account the balance of your classes. So you weight each class based on its representation inside of the data set. And this is what I recommend most of the time. Obviously, if you want each class to have equal representation, that's a very reasonable way to do that. So weight each class based on representation in the data set, and then compute the precision recall as weighted representation. I think I have a link here. Oh, I don't have a slide for it. Let's see. I don't know if that's actually gonna. Okay, so there's this really great article, and which this is credit for all the images I'm using here. Really great article on accuracy, precision recall. They have some good visual representations in here, pros and cons. Talk about the multi-class classification, precision recall, and macro averaging, micro averaging, and weighted eventually, and weighted averaging here. Oh, they didn't say much here, but we could multiply by class. And that's that. If you have one class that represents 2% of the data set, you could apply that weight. And you can manipulate those weights to represent sorry, I lost my StreamYard. There we are. To represent what makes sense for your problem. That's why I prefer the weighted one. Okay. You can take that same concept and you can apply it to the F1 score. Because once we have a precision metric and we have a recall metric, as you guys know, we can take those, combine them, and get an F1 score, which is the harmonic mean between precision and recall, or as you know, it could be an F2 score, an F.5 score, an F beta score, essentially. But let's just start with one. So we could do a macro average, that same concept that we just talked about. Do we macro average? Do we micro average? Do we weight the average? We could do a macro average F1 score. We could do a micro average F1 score, and we could do a weighted F1 score. Let me see what other, categorical cross entropy. Okay. This is it for multi-class precision recall, F1 accuracy. Any questions on multi-class applied to those? Okay. This is not supposed to say mean absolute error. I have a typo there. Categorical cross entropy. This is our, I think we'll call it good after this. So we're going to go, what do we have? 5, 6 more slides. Categorical cross entropy. So also known as softmax cross entropy or multi-class log loss. This is a function that's commonly used in multi-class classification problems, and it measures the difference between the true probability distribution of the target classes and the predicted probability. So this is probably going to look pretty familiar to you guys. So you kind of know this by another name by now, but categorical cross entropy, the reason I put this on here is because this comes up quite a bit. This is a very, very common metric in evaluation of multi-class classification problems. And you guys already know the binary classification representation. So you guys already know log loss. If we take that concept of log loss and then extend it across multiple classes, we get categorical cross entropy. And it's the reason categorical cross entropy is important, the reason it's utilized is the same reason that log loss is so important. It's because it provides a metric based on the probability. So everything else we looked at, F1 score, precision, recall, we're just looking, what did we predict, what was the outcome? Like, what did we predict 1 and was it 0? Did we predict? We're just looking at the classes. We're not looking at the probabilities, which is a really important part of a multi-class classification problem. Because if we're predicting, give me 2 seconds to whiteboard, because it's driving me crazy that I can't do that well on this. Okay, let me erase this confusion matrix. This is important. This is if there's one metric that you guys should take away for multi-class classification, it would be categorical cross entropy. Because it is important that we look at the probabilities. So if we have a model, let's look at where we're wrong here. We predicted 1 and it was actually 0. Well, okay. What if we said, what were our probabilities here? Let's look at, let's make 2 scenarios. Scenario 1, and let's make scenario 2. Okay, in scenario 1, we, let's make a chart here and let's call it probs 0, 1, 2, 4, 5, I had to 6, 7, 8, 9. I had to pick a problem with a lot of probabilities here. So we predicted 0, but it was actually 1. What if our probability here was 0.9 and our probability here was 0.1? And what if in this one our probability here was 0.4, 0.3, 2, 4, 10. Okay. In this scenario, okay, we predicted 0 for everything else, okay? No probabilities for these other things, just because I want to narrow down here. All right, in scenario 1, where our label was 0, we predicted 0. We predicted 0 because our probability output is we predicted 0.9 here, 0.1 here, and 0 for everything else. Remember that in multi-class classification problems, your probabilities sum to 0. In multi-class class, for most multi-class class, I'm just going to go ahead and say it. In multi-class probabilities, sum to 0. So our probability sum to 0. So whatever, and you output a probability for each class. So our model outputs a probability for each class. So when our model is predicting this number here, there is a probability with each and every outcome. We have 9 outcomes here, 10 outcomes here. We have 10 potential outcomes, 10 potential numbers. There's a probability, we just made the other probability 0. This happens in large language models too, by the way, the ChatGPTs that you guys use of the world, next word prediction. There's a probability associated with every token that could potentially be output by that model. It's not the word that gets chosen has probability associated with it. So it's like a multi-class classification problem. So these metrics are important. They lean into that space. These concepts are important. So there's a probability associated with each class. What's also very interesting is I know we talked about thresholds. We talked about, hey, if it's like greater than 0.5, then it's class 1. If it's less than 0.5, then it's class 2 or class 0. That changes. That changes when we look at multi-class classification problem, because let's look at scenario 2 here. Oh, we predicted 0, but wait, 0 only had a probability of 0.4. Yes, but that was the highest probability across all of these probabilities. So we can have a probability that is less than 0.5. We can now have a probability that's less than 0.5 that gets chosen. It's not that we don't have a threshold anymore. There's no more thresholds. Let me make sure that's true. Yes, there's no more thresholds when we look at multi-class classification. It's just which one was the highest value, which one had the highest probability. So you can have your model predicting 0 with really low probability, what I would interpret as potentially low confidence. When I see this, when I see 4, 3, 2, 1, this model's, it's not really sure. It's not certain. This is not a confident prediction into this 0. When I see this one, 0.91, this is really confident. There's a lot of confidence. 0.9, this is it's confidently wrong though. The answer was 1. So that the purpose here is we should penalize this heavier. Because look at the confidence that this had, that was 0.9 versus 0.4. Okay. That makes sense? So far, I haven't pulled up the formula. Not does the formula make sense? Does this concept that you can have model output a probability for each class, the probability sum to 0, or oh my gosh, sum to 1, the probability sum to 1, and that you can have probabilities less than 5 for your target class, less than 0.5. Okay, I'm going to assume that resonates with you guys. If not, let me know. Now let's look at the formula. Okay, so this is a generalization on log loss. Remember log loss? We said it was a switch formula. Sorry, I was thinking I should take a step back, but we'll just keep going. Remember log loss? We said it was a switch formula. It's on or it's off. This is also a switch formula. It's on or it's off. It's just it's a generalization on that formula. So we still have the negative sign at the beginning. Remember the negative sign is going to negate our weird negative numbers that we get. And we have y true times log of y pred. So we're only looking, this y true at I, we're only looking at the probability when it's associated with the class that we're looking at. So if we're saying class A, let's take the log of the probabilities for class A and multiply that with those outcomes. I think I don't have a single slide. Okay. Basically, we're going to calculate that that log loss calculation for each class. You can kind of think of it like that. Yeah, that's a fine way to explain it. We're going to calculate log loss essentially for each class. So we're going to take the log of the probability across each of those classes when the outcome was that actual class. So in the example we were looking at on the board, that outcome was 1. We're going to calculate that probability, the log of that y-pred, where we predicted 0.1, where we predicted, let me just write this out. Okay. In this example that we were just looking at, we're looking at the y true. This is our y true here. So when we're looking at L equals negative some y true times the log of y pred. Okay, we want to evaluate what was the performance here. Well, we were trying to predict 1, so for this, we're only going to look at what was the probability associated with 1. Don't care about the other probabilities, okay? So we're going to take the y, you can ignore the y true now. Yes, it was 1. So we're going to take the log of, in this case, it would be the log of 0.1. In this case, it would be the log of 0.3. And that's what would get added into our formula for this one. So if we're looking at 4 and it predicted 4, we would look at what was the probability associated with that. For this one, where it was actually 2, but we predicted 5, we would look at what is the probability associated with the prediction for the value of 2. What is the probability associated with the prediction for the value of 3? Because our model outputs a probability for every class. Okay. I hope you guys are feeling strongly about your statement that log loss was easier than, what was it, than linear regression. Okay. So categorical cross entropy, we're going to calculate the loss for each instance by comparing the true probability distribution, the one hot encoded vector, with the predicted probability distribution output by the model. Just like log loss, penalizes heavily confidently incorrect predictions. That's the key word there, confidently incorrect predictions. This is a generalization on our log loss metric, so it's quite often used. Categorical cross entropy is quite often used as a training function for neural networks, especially when predicting across multiple classes, multi-classification tasks. Oh, and this is a great video. So I think this video really helps. I would recommend watching until about 5:29. And I have extra sources linked in here as well for you guys. I think we covered a lot today because we sort of mashed 2 things together. So I think I'm going to stop here. Oh, I meant to share back to, let me stop the stream.